Welcome back. So let's continue on the information need and query. So to recap, if you just look at queries, it doesn't make sense to evaluate the system because it's just going to be fully correct. This is math, the power of math, beautiful, right? But information need is different because this is more imprecise, and you might have here some sort of mismatch between the two. So now if you look at the information need and at the results of the system, then things might happen. So the abstraction level that we have is that we have a system that returns a subset of the documents for every query. And some of these documents are going to be relevant. I was looking for the word, relevant to the information need, or irrelevant to the information need. Can you see the difference? So it's careful, light, dark. And we classify these things, relevant, not relevant. And again, I repeat, this is the information need we are looking at. If we are looking at the query, this will all be green here. This will all be correct. But for the information need, although the query returns the documents, they might actually not be relevant to Alice, right? So how do we evaluate the system? Well, we like to compare the size of the relevant and not relevant documents. Of course, we love it when as many as possible are on the left, and we don't like it so much when too many are on the right, right? So in order to evaluate this and have a metric that tells us, we divide the number of relevant results divided by the total number of returns results, right? Again, we only look at the results. What is not returned by the query, we don't even look at, right? But in the resulting documents, we divide the number of relevant documents with non-relevant documents. What is my precision here? We can throw the box to anybody who wants to tell. Okay, oh yeah, here, over there. Maybe we do 2 hops, 3 hops. It's like a network topology structure. 1 hop. And oh wow, in just 1 hop, all right?
It's 1/2.
It's, oh, well, that's sometimes happen with the microphone. It is?
Half?
Half, exactly, this is 50%. Yeah, absolutely. I think the microphone is acting up. Sometimes it happens. And 1 hop and 2 hops. Oh, wow. We're getting good at that. All right. Oh, it seems the frequency of the pop-up is every hour. All right. Okay. So 50% indeed, right? It's 8 divided by 16. All right. So we have a precision of 50%. That's so-so, right? Not great, but yeah. The name that we use for the relevant results that are returned is true positives, right? They are relevant and they are returned, right? Divided by the return results. This is 50% indeed. What's the precision here? Everybody at the same time? 100% exactly. Great. And what is the precision here? 0%. That's absolutely awful. Absolutely awful, yeah. Here? Everybody at the same time now? 80%, exactly. Great, you're great. Okay, indeed. So this is 8 divided by 10. Okay. All right, now let's add more. I'm also going now to throw in the non-return results. So now we have everything there is in the collection, right? Everything in the upper half is returned by the query we are looking at. Everything on the lower half, let me show. This is returned by the query, all of that. This is not returned by the query. This is all the rest. Of course, in practice, this is going to be gigantic and this is going to be smaller, right? So what you return is small. So this is not returned. And then on the left is everything I care about or Alice cares about. This is what I would like to have. And everything I don't even care about, right? Okay. So now there is a second metric that's called recall. The first one was called precision, right? True positives over all return results. The recall is the relevant positives, the true positives over everything that's relevant to you. I forgot to edit the contrast there. So it's basically this right here, right? This part divided by the total, right? It's exactly the same as precision. Precision was that way. So it's 8 divided by 16 in that case. That's the recall. And that's 50% in that case, 8 divided by 16. What is the recall here? It's 100%. Here it's great because I actually got everything I want. right? The query gave me everything. Maybe it also gave me useless stuff, garbage, but at least everything I wanted is part of return the results. Now, here the recall is 0%. The query gave me only garbage. I don't have anything that I can use in the result. This is the worst. In that case, it's 2/3. 8 divided by 12, it's 67%. For whom is that clear? Right. Who can compute precision and recall if I give you matrices like that? Okay, very good. Sometimes there are some in the exam. All right. Now, a bit of terminology. If you look at this diagram here, where you have all the documents organized for a specific query and engine in relevant, not relevant, and return, not return, that gets 4 groups. We love to have documents in there. They're returned and they're relevant to you. We love to have documents in there. You don't care about them, but you also don't get them from the query. That we don't like. The query is basically returning garbage. It's a type 1 error with false positives. They are returned, but you don't want them. We also don't like that. This is something you care about, but the query does not give them to you. This is called a type 2 error or false negatives. I have to warn you, I never remember type 1, type 2. I always mix them, and as the years pass, I keep confusing them. So I have no idea if you just tell me type 1, type 2. Maybe you do a better job as remembering that. I just say false positives and false negatives because this is clear to me. But somehow, especially in machine learning, the machine learning specialists, they will know. If you say type 1 error, they will know it's false positive. Type 2 error, false negatives. Who spontaneously knows type 1, type 2? Some? Do you take the machine learning lecture? Not machine learning, okay, but it's very good that you know that. All right. I insist that this is common with machine learning because when you do classification in machine learning, you have exactly the same metric. You have exactly the same way of looking at things with false positives, false negatives, and so on and so on. So this is one less thing to learn for you because this is in common between information retrieval and machine learning. Well, in fact, information and retrieval and machine learning have a lot in common, really. And there's half of the book is about machine learning, in fact. Okay. Now, this here is a system for a specific query, of course, that has high precision. How do you see it has high precision? There's not a lot of false positives, right? There's not a lot of documents here. So this is high precision. This here is high recall. Why? Because there's not a lot of relevant documents that is missing, right? But as you might have noticed, in practice, you get this or you get that. Typically have some knob that you can turn basically in many systems. You get this or you get that. But perfect precision and perfect recall never really happens. It is very, very tough to build systems that will return exactly what you need. For the information need, again, if you look at the query itself, this is perfect precision, perfect recall. If you just look at the query, it's math. But the information need, high precision and high recall, very tough to get. This is a compromise, and very often you can move the slider depending on your preferences between the two, right? Okay. That's it for today. We'll come back to evaluation in a few weeks and have even more metric with accuracy. You will learn that accuracy is not a good metric, actually, but I'll still show it to you. Sensitivity, ROC curves, and so on, right? So we'll come back to the evaluation of systems. But precision and recall, this is really a must, so I wanted to show it already today. Okay. Now, let's get back to our system. So again, what are we doing? We are building an information retrieval system that works with a collection of books that we call documents, and the user enters a so-called Boolean query with terms that are combined with and or not. And we want to return the documents that, that match this query. We saw a first very naive, I would call it, with an oxymoron, a theoretical implementation with this incidence matrix. As you can imagine, that's not how we're going to implement that in practice. Because if you look at the incidence matrix again, over my slide, there's not a lot of room, so I only put 6 terms and 10 documents. But in practice, you don't have 6 terms and 10 documents. In real life, the number of terms you're going to see is more typically like 500,000 terms. If you look at the web or the Library of Congress, right? So 500,000 terms is not unusual. The number of documents, typically 1 million, but remember, if you look at the British Library, it's more like 170 million. It's absolutely gigantic, the number of documents. That's not even exponential, it's actually quadratic. I mean, it's just a multiplication. But if you do the math, you will notice that there are 500 billion Booleans in there. Now, that might have been a long time ago. Nowadays, 500 billion Booleans is 500 giga. I'm going to try to get that right. 500 gigabits, meaning that's a bit less than 100 gigabytes. So that fits on your laptop, no big deal. But it's very inefficient, nevertheless, to have it like that. Because as you can imagine, you have a query, you have to traverse 1 million documents for every term you're looking for. So yeah. Oh, I forgot to put a capital B. So just a reminder, Boolean is supposed to be with a capital B, with a uppercase. Anyway, how many zeros do you think that there are in there, in this matrix? Yes, almost every entry is a 0. So almost probability 1, you know, there's basically zeros all over the place. If you consider that there's typically 1,000 terms per document, that's 0. Let me try to get this right, 0.02. I don't know. Okay, my brain is too fried to do any calculation, but basically you probably see that there's zeros all over the place, right? So we have 500 billion bits, Booleans, and we have only 1 billion ones and 499 billion zeros. This is a huge waste of space, basically. So any information theory specialist will tell you that can be compressed, right? The entropy here is pretty low. So this is highly inefficient, and you don't want to store it that way. Oh, there you go. I was not far away, 0.2%. It was 1 zero too much. So 99.8% of that is empty, 0. So how do we improve that? Well, yes, absolutely. We can store it in a better way. I think I had a question that asks for the better way, but let's see what I wanted to ask here. Oh, yes, I do have a question that asks you, how do we solve that? So tell me how we solve that. How do we solve the 99.8% sparsity issue? Okay, the first option is we rent a cluster of machines on Amazon AWS and hope that the ETH finance and controlling department doesn't complain. We list, an S too much. We list only the terms used by each document rather than mark all terms with zeros and ones. Or the opposite, we list only the documents containing each term rather than mark all documents with zeros and ones. Or only Google knows, and you can't tell us. By the way, this is probably a question that you can reverse engineer. Who is good at reverse engineering multiple choice? You don't know about reverse engineering multiple choice. You know that when we prepare multiple choice questions at the exam, we have to anticipate the reverse engineering. Because here you probably figured out that it's answer 2 or 3, right? Just looking at the structure. Anyway. But the question is only the terms used by each document, or you list only the documents containing each term? By the way, there's a trick that some people use for multiple choice. Pick answer C, A, B, C, D, answer C. If people actually do it manually and don't think about it, there's a bias towards answer C. But for the exam, we shuffle, so that will not work. But in general, it's a good trick. That answer C is increasing the chances. Okay. Okay, that might actually have been a hint for this question because it turns out to be answer C. These ones, I do not shuffle the clicker apps, so maybe that works. Just the exam we shuffle. All right, so indeed, for every term, we list the documents that contain it. That's how we do it. Consider the reverse just for a moment. For every document, we list just the terms that it contains. This is the original collection, if you look at it that way. If you look at document by document, and every document, you list the terms that are in the set, then this is the original collection. But answer C, there is an inversion here. It's the other way around. You start with the terms and list the documents that contain that. There is a notion of inversion. It is very important because of what I'm going to show you now. Let me see if I get that one right. I think it's 5 now. Yes, that's where we were. So now we get rid of the zeros. And for every term, so that's every row, we only store the documents, more exactly the document IDs that they contain. This is what we get. And you might have noticed the name of that, inverted index. The reason we call it inverted is precisely because we start with the terms and list the documents. If we had instead listed the terms in every document, even though the order doesn't matter, that would not have been an inverted index. Who understands that? Okay. In fact, in databases, there's always this notion of inversion. When you create an index, you always invert it. You basically compute offline the inversion and then materialize the inverted structure somewhere, and then you look up in the inverted structure. So this is why it's called an inverted index. Some people call it an inverted file. Okay, this is the same thing, really, as the matrix we've seen before. There wasn't, I don't have it on the slides right now, but basically we just dropped the zeros. We still have 6 terms in my examples. These were the 6 rows, but now we have something different. It's no longer a matrix. It's more like a linked list, if you want to call it after some structure. It's a linked list of integers, of document IDs. So document term T is in documents 1, 4, 9, and 10. Before that, in the matrix, we would have had zeros everywhere except in 1, 4, 9, and 10. Now we really have explicitly a list of integers right there, a linked list of integers. By the way, the fact that this is list of integers makes it quite cool to study, and we'll spend an entire week on this notion of lists of integers, right? But we are keeping that aside from now. This is an inverted index. Okay, now I would like to introduce terminology to you, and I'm going to be as precise as I can to be very, very clear on what we call what. This here is a term. What we call a term is really what appears on the left of an inverted index. How term relates to the tokens, meaning what you find in the original documents, we'll discuss next week. Because somebody observed during the break, that's a very good point, that if you have conjugated verbs, right, like spiele, spielt, spielt, spielen, and so on, you could consider them the same term, spielen, right, and then put a single term there. So formally, what we call a term is really what you have here on the left of your inverted index that is part of your abstraction, but there might be something non-trivial going on when you actually extract the terms from the documents, right? So that's for next week. Anyway, that's a term, and we have 6 terms there. This here on the left is called a dictionary. So now in my screen, it looks simple. It's just a stack of six terms. In practice, there is a data structure behind that, but that also will come back to it. What exactly, you can already try to figure out what kind of data structure you want to organize them in. But for the purpose of this display, we don't care yet about the data structure, right? We just have these 6 terms right there. And this is called a dictionary, right? And again, when we say dictionary, it typically includes the data structure behind them. Dictionary is really the overall terminology for that. Next. This is a document. What do I mean with this? Because I actually put 3 rectangles here. This here is document 4. You might have noticed that document 4 appears multiple times. It's going to appear every time there is a term in it, right? So since document 4 contains T, V, and X, it appears 3 times. but the document is really 4. That's it's the 4-ness of the documents that basically matters here, right? So this is document 4. Documents have document IDs. I already said that. We abstract away documents with IDs. There's document 1, document 2, document 3. It's completely arbitrary how we order them. It's just some sort of internal reference that we use, and we do it on the fly when we process the collection. Okay, this is a document, document 4. If I only look at one single one of these 4s, this is called a posting. It's a posting, but be very, very, very careful. The posting here is not just 4. It is actually a pair X4. A posting is a pair with one term and one document. A posting is the presence of one term in a document. There are as many postings as blue rectangles there, right? I think in object-oriented programming, you could call it a use, right? Some people call it a use. So a posting is really a pair. In that case, the posting we are looking at in this rectangle is X4, but it's just that we don't actually put X4 in there. Why? Because we are clever and we just put X1s over there. We don't repeat it, right? Otherwise, we could have said X1, X3, X4, X7. That would be a waste. We optimize a little bit and put the X there. But it doesn't change anything to the fact that if you just look at this rectangle right here, mathematically, it is a pair of X and 4, not to be confused with document 4, right? You could, if you want to sound smart, you could say that here a document is an equivalence class of postings that have the same ID, right? Okay, anyway, document, posting. This here is called the postings list. This is the name we give because it's a linked list of integers, a linked list of document IDs. So it's a postings list. And in the postings list, these are all pairs, but they all have the term in common. They all have term X in that case. This is a postings list. These here are called the postings, right? So you have the dictionary on the left, the postings on the right. And this here is called the index, right? So I threw all of that at you, right? All of these vocabulary. So there's term, dictionary, document, posting, postings list, and postings, and index, right? I'm trying to be as precise as possible, and I'm going to try to stick to that terminology, right? But you will see in practice, and even in the book, sometimes you have to be prepared that sometimes you have, when you speak casually, you might not exactly stick with that terminology, but I'll try. For whom is that clear, this terminology? All right, make sure to be familiar with that and to learn that by heart. Okay, oh, what's happening here? I'm adding something here. It's in purple, it's not blue. These are frequencies, more exactly document frequencies, and we'll spend also an entire week dedicated to these things. What is that? Can anybody guess? What are these integers in here in purple? Yes? Yeah, exactly. This is the amount, the count, the total number of documents that there are in the postings list. It's the length of the postings list, if you want. 4, 1, 2, 3, 4. 3, 1, 2, 3. 6, 5, 1, 2, 3, 4, 5. 1, there's only 1. 4, 1, 2, 3, 4. 3, 1, 2, 3. And then you can see the highest number right there gives you the most frequent term. Okay, the term with the highest document frequency. Now you might be confused. Why don't I call that term frequency? Well, it's because term frequency means something else entirely, but I don't want to confuse you with that. So this is why I put document in gray here. Just remember that these are the counts and the length of the list, and that's it. And then in a week, a bit later, we'll talk about all of these statistical computations on frequencies. All right, and we'll do that together with linear algebra and vector spaces and dot products and so on. It's actually quite an entertaining lecture. All right, this is the inverted index. Look at it closely. We're going to see it. The entire semester is going to be all over the place. At least for the coming weeks, we are going to look at it from all angles at this inverted index. All right. Can we reconstruct the original collection of documents with this index? No, we can't. I see a few of you nodding. No, we can't, because we don't know about the order of the terms in a document, and we don't know about the number of occurrences. This is the set of word semantics. So we lose information in there. It's more compact. than the actual original collection. Okay. Okay, let's now try to build that on a concrete collection, because now I just made that up, right? That doesn't come from anywhere. I just randomly put numbers in there. But let's take an example that is actually in the information retrieval textbook, document 1, 2, 3, 4. How do we do that? Well, first you notice there's punctuation with commas and so on, right? There's even uppercase. So let's do it simply for today, and we'll talk about next week about the details of that. But basically, let's just use the spaces as an easy way of tokenizing. It's called tokenizing. So we tokenize the documents with the spaces, and we get tokens, not to be confused with terms. The tokens are really the ones you really get from the original documents as the characters in which they appear. So of course, now tokenizing is used in other contexts like crypto for other things, but in this very context, this is what it means. Okay, next, we do a few things like it's called linguistic preprocessing. We'll talk about that next week. So let's put all of the uppercase letter in lowercase, to simplify things, getting rid of punctuation and so on and so on. It's a bit oversimplified, but it gets to the point. Now, I'm going to assign document IDs, meaning that I'm going to put 1 here, 2, 3, 4. And now I'm regrouping, I'm swapping the columns and rows. This is exactly the same thing, just swapped. I kept the colors. This is document 1, document 2, document 3, document 4. Now you see the pairs. This is a pair, a term and a document. So these are technically postings, right? These are technically postings. We'll see later that these are positional postings because we didn't eliminate duplicate just yet right now. But anyway, these are pairs of terms and documents. What do I do next? I sort it alphabetically by term, right? So this is sorted, this is grouped by document. I just shuffle this around and sort it alphabetically by term, but I keep the pairs together. For whom does that make sense? We're still following? Okay, I sort it, and then I group it. So you see 3 times the same term in here. So now I group them. This is what happens now we get closer to the inverted index, right? I just repeat the term once, and then I have a list of the document IDs, right? And I did it at other places. You see our 312. Now I just also reorder the document IDs by increasing number. And now I just, that's just some cleanup cosmetic here that I'm doing, right? And basically, I'm actually, and now I add the frequencies, these purples with the counts, right? And that's it. And I have an inverted index. And now I put terms because now these are the terms, right? Here it was the tokens when we look at the documents, but when I do the elimination and pre and post-processing, these are terms. Okay, for whom is that clear? Okay, this is an inverted index. This is the same thing as what we had here, right? But now we specifically built it for that collection. Of course, we simplified a lot of things, but this is it. Now, how do I query stuff? Well, that should be easy, so we can quickly go over that. If I want to query our, all I need to do is look up our, right? It's right there, and I return documents 1, 2, 3. And most systems will actually keep the documents stored somewhere, and they show you snippets, right? So that you will get the snippet of document 1 with our highlighted. This is basically going the extra mile for the developer of the system, right? So our returns documents 1, 2, and 3. Now, how do I do the end? Our end com. Well, I just look them up. So our is here and com is here, right? So we have 1, 2, 3, 4 for com and 1, 2, 3 for our. And now we have a Boolean. It's an end. It's a logical end. How do I do an end? What do I compute between these two lists? Yes, the intersection of the two lists. And or would be the union, right? Okay, so I take these two lists, I intersect them, and you see that only 1 and 3 are coming out of this intersection, 2 and 4 none. No, because they are not in both, right? So the intersection gives me 1 and 3, and then I can display documents 1 and 3, and indeed, you notice you can highlight com and our in these two documents. They are both here. So this is a way to check correctness too, okay? Or it's the same, our or this. I picked both of them, but this time I compute the, all at the same time, the union, exactly. I do the union. Oh, that's all the documents in that case, 1, 2, 3, 4, and you see there's either or, either our or this, and I get everything. Okay. Now, let's look closer at the intersection algorithm, because how do you intersect linked lists? You might actually have done that in data structure lectures. Who has ever intersected linked lists? You never did that? Yes, some of you. Yes, I see raised hands. Okay, we can do a PowerPoint karaoke. Does anybody want to do a PowerPoint karaoke? Otherwise, I do it myself. That's fine too. Okay, I'll do it. Don't worry. Okay, so of course, it's not a karaoke for me because I actually made the slides and I know what's next. But anyway, we initialize list A and B. So these are the two terms that we want to compute an AND between. So I initialize with 2 pointers. So I put them right at the start. Right? And now I have some computer program. It's actually quite simple to do this computer program, but you will see it's just iterating. I compare these two document IDs. Are these the same? Yes, they are the same. So I just put it there. Okay. And then I push the 2 pointers to the right. Right? Are these the same? No. So I push the smaller one. What is the smaller one? It's 2, not 3. So I push this one to the right. That doesn't match. Right. Are these the same? No. So I push the smaller one. This time it's 3. Are these the same? Yes, bingo. There you go. 4. Then I push both of them to the right. Is this the same? No, that's 5. I push. Is it the same? 8, 6? No. So I push the smaller one, 6. Is it the same? No. 8, 7. I push again. Is it the same? Yes. So I have an 8 here. Then I move both pointers to the right. 9 and 11, is it the same? No. So the smaller one, 9, is pushed. 10 and 11, is it the same? No. So I push the smaller one, 10. Now I have 11 and 12, is it the same? No. So I push the smaller one, 11. 12 and 12, is it the same? Yes. And there you go. And the end. This is the intersection algorithm of a linked list. In fact, in the past, we did have PowerPoint karaokes. We did have students who tried it in front of the class. All right, so this is it. That's the intersection algorithm. Normally, you should be able to program it. What is the complexity of that? Exponential, polynomial, linear, logarithmic, yes? Linear, exactly. It's linear because you basically traverse left to right. Do we have a question? In Zoom?
So the question is, can this intersection be in place?
Oh, that's a good question. I think, so theoretically, you could always, when you have data structures, you can do in place or not in place. In that case, though, you don't want to change the inverted index, right? Because the inverted index, it takes a lot of time to build, can take hours to build. So you probably don't want to change the inverted index directly in place. So this is the reason why you probably want to have an extra memory space for the output right there, right? But if you forget about information retrieval and inverted indices, then of course you could do the same algorithm in place. What you do is that you just unlink the elements that you want to remove and then relink with the next one, right? So that's basically removing elements from one of the lists that are not in the other one, right? So that's a good question. And again, you would not do it in place just because you don't want to change the inverted index. Yes? Yes, absolutely. Absolutely. We do it before. This is always sorted. It has to be sorted. I actually might have done it very quickly right there, but you saw that this happened where here, you see? When I did it, I actually sorted them. I probably said it too quickly. This is super important. In fact, when we will look at, in a few weeks, at index compression, it's not just lists of integers, it's lists of sorted integers. And the fact that the list is sorted actually gives you an opportunity to massively improve performance in terms of space. So that's a very good point. Thank you for mentioning it. This is indeed sorted. And it is indeed a requirement for the algorithm that the lists are sorted, of course, because if they are not sorted, then that all breaks, right? Okay, what about the union? You want the karaoke? Let me do the karaoke then. Okay, that's the union, that's the logical OR. We start with 2 pointers, 1 and 1. Are they the same? Well, we don't care if they're the same or not, actually, in that case, because that's a union. So we put it anyway, 1. Then, what is the smaller one? Well, it's 2. We put it there. Then we move the smaller one. Now, what is the smaller one? It's 3. Okay, now what is the smaller one? Well, that's twice the same, 4. We move both pointers. What's the smaller one? It's 5. Now it's 6. Now it's 7. We move always the smaller one every time. So that's same as intersection. 8 then we move both of them. Or you see I was running out of space. Well, technically I could have gone further, but anyway, maybe I just wanted to have fun and going like 9, 11, no, 10 is the next, then 11, then 12, and that's it, that's the union, all right? Who is absolutely clear on intersection and union? Okay, very good. So you could program that. Very good. Now we can optimize a little bit because intersection and union is the case where you have just one and or just one or. But in reality, that might be more complex. You might have ETH and Zurich and Bibliopol and so on, right? So there's good news for you because you need to figure out in what order you do that. It's associative, right? So you can do ETH and Zurich and then merge with Bibliopol, or you can start with Zurich and Bibliopol and then merge with ETH and so on. So we have a lot of strategies. What is the fastest one? What is the way that we can be as fast as we can merging intersecting all of these posting lists? Well, we know the document frequencies. So should I start with the low frequencies or the high frequencies? Yes? Why? Yes, absolutely. So we start with the low frequencies here. So you see here, I looked it up. So it's in the inverted index. It's these purple rectangles. ETH has 10,000 as a document frequency. Zurich has 100,000 and Bibliopol 10. So we pick the two smallest ones and we sort them that way. It's a reorganization of the query. And now we are going to merge Bibliopol and ETH. What's the max size of the merge? 10, exactly, it's a smaller one. So you see how efficient that is. And now we are merging a posting list of just 10 documents with one with 100,000. So this is going to be fast. And we'll see next week ways to make it even faster with skip pointers, I think this is called, right? But anyway, if you reorganize that from the lower frequencies to the higher frequencies, you can optimize the frequency here. All right. So basically what you do is you start and then actually coming back to the question, the first one you copy over and then you do it in place. So actually that's a super smart question because now you can do it in place, but in place with the one that is the temporary list in memory, right? Okay. Okay, and now we have the entire list of results. In general, we can have more complex queries with or, and so on. However, if you studied a bit of logic, you probably know who knows about disjunctive normal forms and conjunctive normal forms. Okay, very good. So this is perfect because you can just, I think it's the disjunctive normal form that you need. It's plenty of ors with ends in between. Then you compute the ends and then you can do the ors after that, right? So you can also, if you don't know about disjunctive normal forms, then you can do it in another way by estimating the size. In that case, you sum the two lengths. That gives you an upper bound on the size for or. But I think you would probably prefer the disjunctive normal form to run your queries. How do you do knots? Well, it's just an adaptation of the intersection algorithm, and you just interpret the presence as an absence and the other way around, right? So this is how it works. Right. Now, this is called an EBNF. Who knows about EBNFs? So whenever you have a language in compiler lectures, you can express the language like that. This is a super simple grammar for our query language, right? You have not, and, then, or. This grammar is basically just setting the precedence, right? The way it's done, that there is a not, and then there's you get an abstract syntax tree out of that. What's important is the parentheses that allow you to do it in a fully generic way. So the parentheses override precedence. All right. But in the exercise next week, you'll get that for free. You'll get the implementation of the grammar and parser for free. In practice, you can just write a file that looks like that and use ent.lr or Bison or whatever to get you the Java code or in any language you want. But in the exercise, you'll have that for free, and then you'll focus on just the implementation. Okay, so what we did today corresponds to chapter 1 of this book, Introduction to Information Retrieval. I think it is available on nlp.stanford.edu. This is a collaboration. I think Professor Manning is from Stanford, Professor Schütze in Germany. And they even have slides. I mean, if you want to also look at their lecture slides, you can. But I really ask you to read chapter 1, and that's another angle to what I told you, just to make sure that that you really understand absolutely everything. Tonight is the exercise session. It's mostly going to be a Python tutorial, right? That the TA team prepared for you. So make sure if you already know Python, it's going to be easy. Otherwise, it's just a way of making yourself familiar with Python. You're computer scientists, you can learn any language quite quickly, and that's just going to add one to your list. Thank you very much, everybody. Before we go, we have 5 minutes. I'm just going to ask this question that I like to control, basically. If you are following, based on that, I can accelerate, I can slow down. This should have been easy. I mean, today normally is easy. If you are bored, then wait until the probability and language model lectures. This will be more challenging. So there will be basically for everybody's taste in terms of complexity. Wow, a lot of everything. This is absolutely wonderful. Okay. Okay. So thank you very much, everybody. Enjoy your lunch, and see you next week at 10.